Swayam Prabha. Digital India. Educated India.
Okay, so we are going to start off. I'm going to assume that you all have given it a little bit of a read at least, and therefore in the interest of time and material to cover, I am going to start from knowing that you have read what a partial differential equation is, and you've a little bit read what the Laplacian is. Okay, so I'm going to start from that. I'm not going to try and explain. Please do, if you have not had a chance to read it, please do read it later on. I've tried to sort of distill the idea of what a partial differential equation is in my kind of own way. And hopefully you have some understanding of what a PD is after this, at least, even if you did not have it before. Okay, so we are going to deal with Laplacians and how they could be used in graphics. Okay, so Laplacians, if you have read the note, or are partial differential equations, it's a second order partial differential operator, which features in the Poisson and the Laplace's equation. And PDEs themselves have like lot of applications in physics, in engineering, in mathematics itself. Everything and anything that we see around us could possibly be written down as a partial differential equation. Some of them might be at very small length scale. Some of them may be in so-called continuum limits. Things like Maxwell's equations are in the continuum limit, and most of the physics phenomena can probably be computed as being solutions of some partial differential equations. It's not universally true, but more or less to a first order approximation. Okay, so I'm going to presume you have read that note, or you'll read it later. That's okay. And I'm going to start from here, which is that a Laplacian is a second order partial differential operator. And I've picked these definitions from some very mathy books. Okay, so the definitions are pretty standard, some of them, but there is a book called Partial Differential Equations, volumes 1, 2, and 3 by Michael Taylor. And then there is a book called Manifolds, Tensors, and Analysis by Abraham, Marsden, and Ratiot. So these definitions are from those books, but these are standard enough, so I don't have to refer to those. Okay. So this is the definition of the Laplacian that I might have sort of indicated in the note. It's a partial differential operator on Rn, and it consists of essentially sum of squares of these second partial derivatives with respect to each of the variables. Okay. It turns out you can think of writing this using the vector calculus operators divergence and gradient. So you can write this as divergence of gradient, and this holds true in not just R2 or R3, but in Rn more generally. Okay. So that's one definition. Another equivalent definition is that it's the functional derivative of the Dirichlet integral or the Dirichlet energy. And this involves some degree of variational calculus, which I am not going to get into. Okay. So it's just given for information's sake that this is also a definition. Okay. And then comes the important definition, the one that this talk sort of has it in its title. This is the Laplacian on a Riemannian manifold which has a metric G. Okay. So on a Riemannian manifold, this divergence of gradient, which is true on Rn, is also true on a Riemannian manifold. These operators do take a slightly different definition on a Riemannian manifold. It involves the metric. It's its determinant and its inverse. These are xj's are called vector fields. This is a vector field derived from some function, but it's really should be thought of as a zero form and so on. So all of this is standard definition, and this is how you would define the Laplacian on a Riemannian manifold. Okay. By the way, at any point, stop me, unmute yourself. I'm not looking at the chat, so you'll have to sort of unmute yourself and stop me. Feel free to stop me at any point. Okay. Okay. So all of this is very daunting. Okay. I mean, it looks like it's on a Monday morning. You don't want to deal with these things, and these don't give you really insights yet as well, unless you have equipped yourself with learning some geometry, some differentiable manifolds theory, and so on, and some differential geometry as well. So instead, given the audience, which is a bit diverse and has undergrads from second year onwards to master's students, MSc students, maybe even a few PhD students, it's not a level playing field. So we should start with something simpler. Okay, so that's what. So the idea that I was saying, at the end of this talk, you should have some understanding. You should go away with some understanding of how PDEs are sort of set up and solved in graphics. And this morning session is what is going to set you up for the hands-on applications that we'll deal with in the afternoon. Okay. Okay, let's
I have a question here.
Yeah.
So in the last slide, when you're talking about this matrix G on Riemannian manifold M, this matrix G is something like distance between the 2 points on the manifold, or?
A metric is a device that can help give you the distance. So you can plug in quote unquote 2 points into the metric. It's a bilinear form, and it will spit you out the. Really, it's going to not. I mean, it's not going to help you compute the distance directly, but it can help you with it. Yeah. So the metric is related to the distances. Yes. Sorry.
I mean, my objective behind asking this question was, what's the significance of metric G here? What does it represent, actually?
So the metric is what helps you sort of write. Okay. So if you ask me, I would say that the metric gives you a volume form. So there is something called as a volume form. And the metric is what helps you integrate things on manifolds. And then you can use that integral to sort of compute distances between points if you want, and so on. But the metric essentially is this bilinear form that helps you write down integrals. Okay, so there is a theorem which says that there is an isomorphism between a metric and a volume form. And so if for us, we'll live in a nice, easy world. We'll think of a metric as this diagonal matrix, and the diagonal matrix entries are all 1. That corresponds to the flat metric of Euclidean spaces.
Okay. So, I mean, here the G would be something unique for a particular manifold M. This is how it is defined, or?
No, just like given a vector space Rn, there is a standard inner product, but I can define my own inner products on that space as well.
Right.
Likewise, every Riemannian manifold comes equipped with a so-called standard metric, but there are infinitely many metrics possible on any given Riemannian manifold.
All right. Okay, thank you.
Okay, but there is a standard metric, or canonical metric as it's called. Okay, right. So if you're expecting more on these lines, unfortunately, this is the only slide where the metric is going to show up, because of because of the way I'm treating this. So there is no metric. We will think of the Laplace as div grad, and in any case, most graphics work, I mean, almost all graphics work I know of is done in 2D or 3D domains, Euclidean domains. So this particular form of the Laplace Beltrami will not show up in the rest of this talk. It's only there for information's sake.
Is it like a scaling factor then? Like, can we imagine?
No, like the metric is a point. It can in general vary from point to point. It's not a scaling factor.
Okay. No. So it is like a weighted scaling factor sort of thing, like weighted. So like instead of our regular identity matrix, if we are putting some weights on that, we can probably get different metrics.
Okay.
Something like that.
So if you want, then you're sort of weighting some quote unquote directions when you're computing integrals, which means there might be, so if it's just a diagonal with different weights on the diagonal, you could imagine that your space has some what is the anisotropy? It's an anisotropic space. Okay.
Yeah.
For instance, the on a hyperbolic space, there is a standard hyperbolic metric, which makes even like a finite dimensional Euclidean disk to be like at infinity. Okay, so it's kind of therefore like related to distances. So there's again, for you to, if you have not heard of or seen this before, a hyperbolic space are these spaces with curvature which can be negative or which is negative, and then there is a so-called Poincare disk model of a hyperbolic space, and it's just a two-dimensional disk, and yet the boundary of the disk is at infinity. Okay, and that comes because of the choice of the metric on that hyperbolic space. Okay. But okay, let's move on and hold some further questions in this met relation for a little later. And I'm slightly struggling with my, okay, that's fine. Okay, cool. So let's start with something simpler, which is Laplacian on just the line. Okay. So the note did not talk about it, but in order to apply this Laplace operator, this d square by dx square, even the simple second order derivative to some functions, those functions have to satisfy some requirements. So if you want to think about it mathematically, otherwise like bad things can happen. So the requirements usually are that the function should decay to 0 as your x, this is a small mistake. It should have said absolute value of x. As x goes to plus or minus infinity, this function should decay down to 0. Okay. So physicists might then say that the energy in the function is finite, or in the language of math, you'll say that the function is in the L2 space on R, and this is what is the definition of the L2. So you can see this red pointer of mine, right?
Yes.
Okay. So you might have to speak out, because unfortunately I'm not monitoring the chat. Okay. So this is the definition of something being in L2, which means that this integral u square over minus infinity to plus infinity is finite. And you can slightly use a small little lemma or whatever claim you can prove that it's equivalent to saying that the absolute value of this function has to be finite. It cannot be a function like tan x, for instance. Tan x is not an L2 on R because it blows up. Okay, so functions with singularities are not in L2, but functions which have discontinuities are in L2. Okay, as long as the magnitude of the function everywhere is finite. Okay. So this operator can therefore be applied to functions which decay as you go to infinity, but it can also be applied to functions which are so-called compactly supported, which means they are 0 on most of R, except on some compact sets in R, which are closed and bounded intervals for us. In R, its compactness means closed and bounded. Okay. So some people will call such a function as being an L log 1, locally L1, but I'm going to avoid complexities and say that these are functions which I'm going to say is L02. Okay, these are L2 functions which decay, let's say beyond -1 to 1, they are 0. So between -1 and 1, they are defined. And as an example, so everywhere except between -1 and 1, they are 0. Okay, so we need a function which is compactly supported and L2 and twice differentiable. So those are the functions that we can apply this one-dimensional differential operator on. Okay, so you can't just apply it willy-nilly to anything. Okay, so but at the end of the day, all our physical problems, whether it's in physics or in graphics, the real action or the setting is in some subset of R, not all of R. Okay, so there are these complications, but maybe again this is still a bit too much. Let's start with something even simpler than this. Okay, so I'm going to start now is when I'm really going to start. That initial part was to set it up. Okay, so now we are going to talk about Laplacians on 0, 1. Let's say on some compact subset of R, which is a collection of intervals, union of intervals probably, but without loss of generality and interval. And again, without loss of generality, we'll just choose this interval to be 0, 1 because we are trying to understand ideas here. Okay. By the way, again, I mean, if some of you are joining in a little late, it's because of the diversity of the audience. I'm kind of talking about things in some basic math level. If you find this too basic, my apologies to you. And I'm hoping that some of you who do not know anything about solving PDEs will at least get some sense of it before you jump into applications. But if this feels like a little bit too basic, you have my apologies. Okay, so without loss of generality, we are going to start with the Laplacian on 0, 1, which is a subset of R. Like I said, there is this equivalence. Bounded functions are in L2. So it's enough even here for 0, 1 functions to be just bounded to be in L2 of 0, 1. Okay, so L2 of 0, 1 means that same definition as before. Instead of putting R, I'll just say 0 to 1. The integral is from 0 to 1. U squared dx is less than infinity. Will give me L2 on 0, 1. Okay, so if that's finite, that's an L2 function. But so it's not enough that it's just an L2 function. It still has to be twice differentiable. This is like high school calculus, that if I have to apply this to a function, it has to be at least differentiable once and twice if I have to take two derivatives. And functions which are twice differentiable are denoted as C2. And maybe you've seen it popped up in some context during this last week, I don't know, because graphics people also care about C1 surfaces, C2 surfaces, and so on. So maybe there was a reference to it, and if not, you say something is in C2 if it is twice differentiable in this 0, 1 interval. Okay. Okay, so this is where we are. This is our set of all functions to which we can apply this d square by dx square operator. And this set is usually denoted as H201. Okay, it means that, and I forgot to put this definition, it means the function is in L2, its derivative is in L2, and its second derivative is also in L2. Okay, I need its derivative to be in L2 to sort of rinse and repeat the argument about applying the derivative. Okay, so once or twice I might keep referencing the notes because I wrote it up and took me a little bit of effort. So if you had read the notes, you would have noticed that a problem like this would require a boundary condition. Okay, it's a problem on some compact domain, then it needs a boundary condition to be well posed. Okay, and there are many choices of boundary conditions. You can say that the solution, unknown solution U, should take value 0 on x is equal to 0 and value 1 on x is equal to 1. It's called as the all-Dirichlet boundary condition. It can be Dirichlet on the left boundary and so-called Neumann. Neumann means this is the boundary condition. The derivative with respect to x is set to be 0. It can be Neumann on the left and Dirichlet on the right, or it can be an all-Neumann boundary condition. So du by dx is 0 on both x equal to 1 and x equal to 0. Okay, and again, you might wonder why I picked 0. It turns out without loss of generality. Whenever a mathematician says that without loss of generality, it means that if this is some other non-zero number, you can handle it. It's no big deal. Okay, so for understanding purpose, it's enough to just consider 0 boundary conditions.
Okay, quick question.
Yeah.
Okay, can it be both, as in Dirichlet and Neumann?
At a given point, yeah. Yeah, you can. Yes, you can take that. Yeah.
A boundary can be varying at some rate, and it can also be at that value at that point. As in, it can be held at that value at that point. But overall, it is actually in space. It is varying, but at that point, it is holding something of that sort.
Okay, so I will sort of deconstruct your question. So the first question was, can it be both Dirichlet and Neumann at a point? Yes, that is one of the many choices which I have not listed. You can take Dirichlet at x equal to 0 and Neumann at x equal to 0. There will be no boundary condition needed on x equal to 1 in that case, okay? the question you are asking is like, can I have a domain which is changing, but at a point the domain is held fixed, right? Maybe that's what you're asking. Slight variations, like we are dealing with functions on domains. The identity function on the domain, if you want, the domain itself is a function on the domain. So you're right. You can hold a point fixed and say that that's a Dirichlet boundary condition. In fact, that's what people would do if you're like smoothing a mesh and you want certain parts of the mesh to not change. Okay, maybe there is a good reason why you don't want certain features of your mesh to change when you smooth it. So you might hold that as a Dirichlet boundary condition. Is that making sense? Does that answer your question? I don't know.
Because why I asked this question was because while reading up on this, I also came up on a particular condition called Robin boundary condition, where they added both.
That's right. So a Robin boundary condition is it's not both. It's a mix of Dirichlet plus Neumann. So that would, okay. So I tried to sort of, I don't, Aditya, can you let me in on my iPad as well? It's waiting for you to let me in. So once or twice I can switch to writing, but for now I'll just speak it out. Yes. So thanks, Aditya. Thank you. So yes, you can give a combination of so-called Robin boundary condition, which will say something like u at x equal to 0 plus du by dx at x equal to 0. The combination is 0. Okay. And if I don't know what your background is, but if you're an electrical engineer, it turns out that Robin boundary condition is quite important. Electrical engineers study, for instance, radiating antennas and whatnot, dipoles and whatnot. And the radiation sort of escapes off to infinity, and you sort of model it by so-called absorbing boundary conditions. Okay, and the Robin boundary condition is an instance of an absorbing boundary condition, or the absorbing boundary condition is an instance of Robin. I don't know which, either way it works. Okay, so the point is.
Okay, I came across it in the heat equation context actually, but okay.
Yeah, in the heat equation also you might say like, that it's kind of, it has a certain flux that's going away. That flux is dependent on how much heat is escaping. Perhaps that's one interpretation I can think of the flight. Okay. So yes, there are other boundary conditions. There are many other boundary conditions, but these are the standard basic ones. So we'll deal with these for now. Okay.
Kaushik,
Yeah, go on.
Sorry to interrupt you. I
Yes,
think
please.
using your iPad, you're trying to join some different meeting. I think that meeting was.
I see. Okay. That's okay. Okay, no worries. Okay, so let me, if needed, I'll figure out how to do this.
So if you just join through your iPad using this particular meeting link, you should be able to get in without any problems.
Yes, I tried doing that. I just clicked on the link in the mail because initially I was trying to.
Just ensure it. Maybe if you have that scheduled PDF, there is that link on the top of
Yes,
that PDF.
I think I took it from the email, which is perhaps the same as schedule. And it does say ACM Summer School on Shape Modeling. I'm at least in, but I don't know if what is happening. Okay, maybe.
So that the meeting that you chose on that other device was I think the meeting
Okay,
of
let me
12
go to
on
the
Thursday.
schedule.
I think. Yeah.
Yeah, you're right. Maybe that could be it. That is my bad. Sorry about the pause, folks. I'm taking care of this technical. Okay, now I think I'm here. Okay, sounds good.
Yeah, you're in.
Great. And let me see. Got it. Okay. Okay, if needed, I can try. This is just trial.
Yeah, we can
Okay,
see.
so yeah, okay, if needed, I can come back here. Okay, sorry about that interruption again, folks. So I'm back to the screen. Okay, super. Okay, let's keep going. And so we are going to, so we have Laplace, this Laplacian operator in 1D on 0, 1 with boundary conditions. And we can define two kinds of problems. One is called as the Laplace's problem, and the other is called Poisson's problem. So if the right-hand side is essentially is 0, you call it a Laplace's problem. If the right-hand side is some given function f, you call it a Poisson's problem or a Poisson equation. Okay, so how do we solve them? This was not in the notes, so I'll have to tell you how to solve them. So we need to use the boundary conditions to be able to solve them. There's this notion or concept called as well-posedness, and it's not well-posed if without the boundary conditions. So we'll throw those boundary conditions in, and for the purpose of understanding, let's just stick with this 0 Dirichlet boundary condition, both at 0 and 1 Dirichlet with 0 value. Okay, we are still not there because we need a right-hand side function here. So let's throw in a right-hand side function, something that's nice and easy to integrate, as you'll see. So that's my Poisson problem, and this is my Laplace's problem, and we're going to solve them. How would we solve them? We just integrate this. In this case, it's straightforward. So integrate both sides.
What is a right-hand side function? Can I?
Okay, so like I said, a Poisson problem is Laplacian u equals a given f. Okay, so I said something to the effect that a partial differential equation is something which tells you about relationship between the function and its various derivatives, such that that relationship equals a right-hand side function. That's the definition of a partial differential equation. And the Poisson equation is when the Laplacian of u equals a given right-hand side function.
Okay, so right-hand side, by right-hand side function, you mean f is the right-hand side?
Yes, yes, because on this equation, there is a left-hand side of the equals and right to the equals. So yeah,
okay,
it's
I was
standard.
thinking that was some new thing you were adding to well
No, no,
posedness.
okay, yeah,
I
just
got
like, yeah, this is just right-hand side literally in this function. Okay, so we integrate,
Sure,
straightforward to integrate both these things. After the first integral here, you get a constant, I call it a. Here you get minus pi cos pi x plus a, integrate once more, and you get use x plus b and use sine pi x plus ax plus b. And these are a and b are so-called integration constants or just constants. And these pick out a family of solutions. And so if you want to know what is the solution corresponding to this boundary volume problem, you apply the boundary conditions, and we get for the Laplace's equation, it's kind of now in retrospect, it's obvious that the solution is 0. I mean, the value of function on both these bounding points is 0. In some sense, an intuition might be that, okay, if it has to have the second derivative 0 as well, it could be something funny, but yeah, in this case, it's just the 0 function. Okay, because this right-hand side is 0. Over here, you get something. You get sine pi x, which I have not plotted, but you can imagine plotting using Wolfram alpha, for instance. And you would see that it is indeed 0 at x equal to 0, x equal to 1, and its second derivative equals this. I mean, we did, after all, get it by integrating. Okay, so what if we had other boundary conditions, right? So for the Dirichlet plus Neumann case, you can go through this process. You'll get, again, 0 for the Laplace's equation, some slightly different result for the Poisson equation. And then I can do this other Neumann plus Dirichlet, and the solutions will be something you can just convince yourself that the constants of integration evaluate to whatever pi and minus pi in this case. Okay. Okay, what about the Neumann plus Neumann case? Okay, and here is the first interesting to a mathematician result, and it's not interesting if you're a graphics person. Turns out this problem is not well posed. Just saying that the specifying only the derivative boundary condition on both the boundary points in this case cannot lead you to solve the problem. Okay, and maybe I talked about it a little bit in the notes. I don't quite, yeah, I think I talked a little bit about it. But yeah, you need, maybe not, I don't know. you can't just do with this. And one remedy for this is to seek the solution to be orthogonal to the space of constant functions. Again, now I'm kind of probably losing a few of you, but stay on, please. These are statements for completeness purpose. Okay, and you can solve this problem, make it well posed by doing this fix because of some deep reasons, okay, which we will not, of course, get into. This is a more elementary level course or descriptions. So there's some algebraic topology, which is a field in mathematics that kind of pops up here in studying analysis, and there are reasons with these so-called harmonic functions and how they are related to the topology and so on and so forth. And that is a reason why you need this orthogonality to the space of constants. But if you're an engineer, and if you're, say, studying fluid flow, maybe, people deal with this Neumann case, and engineers tend to impose what's called as a consistency condition on U, which simply says that the integral of U is 0 on the domain, which means roughly it has same amount of area, which is negative and positive. That's exactly what it means. So essentially, its mean value has to be 0. If the mean value of the function is 0, you can sort of solve even with the Neumann case. So this is like a third condition if you want to solve the Neumann case. And so that's a little exercise you can try later on at your own convenience. You can use this additional constraint and try and solve both the Laplace's and Poisson's problem for the Neumann boundary condition.
Is it again a generalization, as in this consistency condition to be 0 and not any other value, or is it like?
No, this is not a generalization. So the consistency condition has to be equal to 0. Is that, if that is what you're asking?
Yeah.
This cannot be non-zero. Yeah, that is not said to be. That's not equivalent to this so-called deep reason that I'm saying. There is an equivalence here. This condition is the same as saying it's orthogonal to the space of constant functions. This is the L2 inner product, if you want, between U and constant functions. But yeah, but there is a generalization to higher dimensions and manifolds and so on. But yeah, if you want to talk about it, hit me up later on and we'll talk about it. Yeah. Okay. Cool. So what we have done so far is analytically solve Laplace's and Poisson's problem over a bounded domain in R. Okay. And for a Laplace's problem, there's nothing else to do. I mean, you just saw you can just doubly integrate it twice more or less and get away with solving it in 1D, nothing fancy going on. But for the Poisson's problem, you could end up easily with a case where the f is not integrable directly. Okay, I just picked a nice f for the previous problem so that I could integrate it. But more or less for real setups or whatever, I mean, whichever application we're thinking of, a right-hand side function is not going to be integrable. So one way of dealing with it is sometimes you might be able to express the integral in terms of special functions. There are like a bunch of these hypergeometric functions, airy functions. What else can I mean, the one that is escaping my mind right now is, okay, there are a bunch of other functions that are, yeah, the Legendre functions and so on. Yeah. So there are a bunch of these, you might be able to express it in such, the integral in such terms. And that's what sort of textbooks in engineering mathematics, or in early in your engineering career, if you have a math course, that's what you might learn. You might learn sometimes special functions as a whole course in and by itself, although I think that's going away. It used to be a thing in the 1950s and 60s. I think it's already gone away, so more or less, yeah. You might sometimes be able to express series solutions, kind of think of it as Fourier series if you want, express the function as a Fourier series and try and probably integrate it and hope that the series converges. Okay. If not, we are kind of stuck, even in 1D, even on a simple 0-1 domain, even with something as simple as boundary conditions 0-0. If your f in the Poisson problem is not integrable, you can't solve such a simple problem. Okay, we have hit a roadblock. And then it's the time for numerical analysts to shine here. Okay. Again, maybe some of you have already taken courses in numerical methods, numerical analysis, scientific computing, whatever they are called in your institute, university. So you might have seen something like this, but I'm hoping, if not, I'm at least reaching out to a few of you who do not know what this is. Okay.